So, what if I told you that the next massive trillion-dollar tech investment isn't actually a piece of software?
Right. It's definitely not some new app you can download.
Exactly. It's not a sleek new app, and it's, certainly not a revolutionary standalone gadget that fits in your pocket. Instead, I want you to picture like a 150-acre concrete slab.
Just massive.
Yeah, massive. One that consumes as much power as a small city, filled with these huge industrial cooling towers and thousands of miles of fiber optics. Because that is actually where the smart money is flowing right now.
It really is. It's a complete inversion of how we've been taught to think about technology really over the last 20 years.
Yeah, for sure.
Because the dominant narrative for so long has been, software eats the world, everything gets smaller, it gets lighter, it becomes invisible.
Right, the cloud.
Exactly. But to power the next generation of artificial intelligence and advanced computing, we actually have to build the largest physical structures in the history of the digital age.
Welcome to today's deep dive. Our mission today is to really unpack this massive shift, to understand why the future of the digital world is basically built on concrete, steel, and megawatts.
And we're grounding this entire conversation in a really fascinating source.
Yes, we are. We're basing this on a phenomenal 2026 book called The Compute Shift, The Convergence of AI, HPC, and Quantum Systems. And I have to say, the most compelling part of this book is actually the person who wrote it.
Oh, Nishant Prabhakar.
Yeah, Nishant Prabhakar. Because he is not your typical, Silicon Valley tech theorist sitting in a lab dreaming about futuristic microchips.
No, his background is exactly why this book cuts through all the usual noise.
Right. He is an absolute heavyweight in the world of global capital. I mean, we are talking about someone with over a decade of deep experience in private equity.
Managing massive portfolios.
Exactly. Yeah. Asset portfolios that exceed $2 billion.
Yeah.
He's worked with major global investment platforms, Premji Invest, the Edelweiss CDPQ Fund, the Rohatyn Group, and on top of all that, he's an active advisor to a global high-performance computing company.
Which means, he evaluates technology through this incredibly ruthless, analytical, private equity lens.
Yes.
He just completely strips away the usual tech hype. He doesn't obsess over the, granular, microscopic technical specs of a new processor.
Right, he's looking at the big picture.
Exactly. He steps back to look at the macro direction of capital and infrastructure. And his core thesis is it's brilliant. He says computing is no longer just a business tool or even an operational expense.
That's a fundamental shift.
Yeah, compute power is the new heavy industry, and building these massive physical compute campuses is basically the ultimate infrastructure investment play of our lifetime.
So if you're prepping for an investment meeting, or trying to spot the next massive market shift, or even if you just want to understand the physical reality behind the AI models you use every single day, you really need to hear this.
Absolutely.
So let's unpack the first major premise of the book. Because to understand why we need these massive campuses in the first place, we have to understand how the nature of the computer itself is fundamentally changing.
Right, and that starts with dismantling a very popular myth.
Yeah, the God machine myth. I always thought, just based on reading headlines, that one day a standalone quantum computer would just drop out of the sky.
Just magically appear and solve everything.
Right. Like it would replace all our current laptops and servers and just magically solve every impossible math problem on its own.
Yeah, that is the myth of the God machine, and Nishant dismantles it so well because popular media frames quantum computing as a total successor to classical computing. They suggest it's just going to operate in a vacuum.
But it's not.
Not at all. The reality we are entering is what he calls the hybrid compute era. Future workloads will basically never run on one single magical device.
So what do they run on?
Well, they're going to require classical high-performance computing clusters, what the industry calls HPC, working alongside massive arrays of AI accelerators like your GPUs, and then experimental quantum processors.
All together.
All three of those architectures have to work together in a single coordinated pipeline.
Okay, so it's less like upgrading to a single amazing multi-tool, and it's more like zoning a highly specialized industrial factory floor.
Oh, that's a really good way to put it.
Yeah, think about it this way. The classical HPC system is the floor manager.
Mm-hmm.
It organizes the raw data, handles the logistics, dictates the workflow.
Right.
And then the AI accelerators, they're the heavy-duty forklifts. They don't do the complex, delicate work, but they can move and recognize patterns in massive amounts of material incredibly fast.
Yeah, the heavy lifting.
Exactly. And then the quantum processor is the highly specialized laser cutter. It only does one very specific, highly complex thing, but you absolutely need the manager and the heavy lifters to get the material to the laser cutter in the first place.
And, crucially, to verify the cut afterward.
Right, verify it.
Yeah, that verification step is the critical mechanism tying them all together. It really comes down to how quantum mechanics actually works.
Okay, lay it on me.
So a classical computer gives you a deterministic answer, right? A 0 or a 1, it's absolute. But a quantum processor operates on probabilities. Its outputs are essentially probabilistic guesses.
Huh, I didn't realize that.
Yeah, because of that underlying physics, a quantum processor cannot exist in isolation. You actually need that floor manager, the massive classical computing power, just to verify the results the quantum machine spits out.
So it's double-checking the math.
Exactly. The classical system has to run validation routines, it repeats calculations, and it compares results just to ensure the quantum output is actually statistically reliable.
Which means the classical supercomputer isn't going anywhere at all.
Mm-hmm.
It's actually becoming more critical because it has this massive job of babysitting the quantum machine.
Babysitting is the perfect word for it. And when you realize that all these systems must operate in tandem, you hit a massive physical wall.
The infrastructure shift.
Right. You cannot just drop a coordinated factory floor of HPC clusters, thousands of AI GPUs, and cryogenic quantum devices into a standard commercial office building.
No, definitely not. Which brings us to the geography piece. If we're building this massive coordinated hybrid system, we have to fundamentally change how we view digital geography.
We really do.
And Nishant draws this historical parallel in the book that completely changed how I view the tech sector.
Yeah.
He points out that, the 19th and 20th centuries, railways, electricity grids, telecommunications, they entirely reshaped economic geography.
Cities basically boomed or died based on where the train tracks were laid.
Exactly. And compute is doing the exact same thing right now. To house one of these hybrid systems, Nishant says a true compute campus requires 100 to 150 acres of land.
Wow.
And it pulls 100 to 200 megawatts of continuous, uninterrupted power.
Which is just staggering. To put that in perspective, 200 megawatts is the energy consumption of a small to mid-sized city.
Running 24 hours a day.
2047, yeah.
But wait, let me push back on this a little bit. Because for the last 10 years, the entire pitch of the cloud was that geography was dead.
Right, the cloud is everywhere.
Yeah, data is invisible. It's stored in the ether. I can access my files from anywhere on Earth.
Mm-hmm.
So why does the physical location suddenly dictate the future of innovation again?
Well, because the cloud was just an incredibly successful abstraction. It did a brilliant job of hiding a very heavy industrial physical reality from the everyday user.
Out of sight, out of mind.
Exactly. You can abstract away software, but you cannot abstract away thermodynamics.
Physics always wins.
Always. Computers run on electricity pushing through microscopic wires. When you pack billions of transistors into a tiny silicon chip and then pack thousands of those chips into a server rack, the electrical resistance turns that hardware into a localized space heater.
Jeez.
You are literally battling thermodynamics just to keep the silicon from melting into slag.
So it's not just about plugging them into the wall, it's about getting all that heat out.
Exactly the problem. And when you scale that up to a 150-acre hybrid campus, standard air conditioning just doesn't cut it.
I would imagine not.
You need industrial chilled water plants. You need these intricate liquid cooling loops pumping directly over the processors. You need redundant power substations because, if the local grid blinks for even a second, a complex simulation that took weeks to run could just die instantly.
Oh, that would be a nightmare.
It happens. And you need dedicated fiber optic corridors trenching through the earth. So suddenly, geography matters immensely. The geography of where you can physically acquire 150 acres, secure 200 megawatts of stable baseload power, and tap into massive water reserves for cooling.
That's a very specific checklist.
It is. And that geography dictates where the next technological superpowers will be born.
Man. So if you're battling physics on a 150-acre site with industrial water cooling, the immediate question is, who on earth has the capital to build this?
Right. Who's writing that check?
Because it's not a couple of software engineers in a garage anymore. The economics outlined in this book are just staggering. Let's contextualize the scale Nishant is actually talking about here. He breaks down the numbers for what he calls a 1 exaflop campus.
And just for context, an exaflop is a machine capable of 1 quintillion calculations per second.
It's hard to even wrap your head around that.
Yeah. It is. To make that relatable, If every single person on Earth did one calculation per second, it would take the entire human race over 4 years to do what this machine accomplishes in a single second.
That is mind-bending power. And the price tag definitely reflects it. According to the book, the capital expenditure, so the CapEx, just to build the facility, is estimated somewhere between $2.6 billion and $4.3 billion.
Billion with a B.
Yes. The data center construction alone, just the reinforced concrete and the cooling infrastructure, that runs up to $1.1 billion. The AI clusters add another $1.2 billion.
And that is before you even turn the thing on.
Exactly. The operating expenditure, the OPEX, is between $250 million and $475 million annually. I mean, power consumption alone eats up $100 to $200 million.
Which basically means you're burning over $1 million a day just to keep the lights on and the water chilled before a single researcher has even run a single algorithm.
Okay, I am really stuck on the economics here.
Yeah.
Because if I'm a typical venture capitalist, I'm used to giving a software startup, say, $10 million, letting them build an app, and then flipping the company in 3 years for a massive multiple.
The standard Silicon Valley playbook.
Right. But this compute campus model feels terrifying compared to that. Why would any private equity firm touch an investment with a $4 billion entry ticket and a $1 million daily burn rate?
Well, this is where Nishant's private equity discipline truly shines. Because he doesn't suggest dropping $4 billion on day one.
Oh, he doesn't?
No, not at all. He understands risk mitigation over these long time horizons. He proposes a modular approach.
Oh, the airport analogy. I love how he frames this.
Yes, explain that one.
So if you're building a massive new international airport, you don't construct 50 terminal gates on opening day if you only have like 3 airlines committed to flying in.
Right, you'd go bankrupt just maintaining empty terminals.
Exactly. Instead, you secure the massive plot of land. You build a runway, the massive power substation, the core network backbone. You build the heavy foundation. But initially, you only construct 3 gates.
And in the compute world, those initial gates are just a smaller HPC cluster and maybe a moderate AI accelerator.
Right. And then as traffic increases, as more industries realize they need this processing power, you simply snap on more modules. You build another terminal. You add a quantum lab.
That's brilliant.
It really completely de-risks the massive capital investment because you only expand the expensive processing hardware when the customer demand already justifies it.
And that modular strategy maps directly onto a very specific infrastructure-style profitability timeline. Like Nishant says, this requires the patience of a toll road or a power plant investor, not a software VC.
It was a long game.
A very long game. He breaks it down into 4 distinct phases. So years 1 to 3 are purely construction. This is massive capital outflow with 0 revenue.
Just digging holes and pouring concrete.
Yep. Then years 3 to 5 are early utilization. So researchers and early corporate adopters start running test workloads. Revenue begins to flow, but margins are incredibly tight because you're carrying the fixed operational costs of that massive power and cooling infrastructure.
Even if the computers are only running at like 40% capacity.
Exactly. You're paying the electric bill whether the machines are thinking hard or just idling.
Right.
But then you cross into phase 3, which is years 6 to 7. This is break even. The ecosystem matures, the schedule fills up, and the revenue finally overtakes those fixed daily burn rates.
And then comes the payoff.
The ultimate payoff, years 8 to 12 and beyond, this is the high profitability phase. Utilization pushes 90%. And because your fixed infrastructure costs are already covered, every additional workload running on that campus drops almost entirely to the bottom line as pure profit.
It is a phenomenal long game. But, okay, if it takes 7 years to break even and costs hundreds of millions to run annually, who exactly is footing the bill? Because the everyday consumer isn't paying for an exaflop.
No, definitely not.
Who needs this much compute badly enough to sign these massive contracts?
Nishant identifies 3 primary revenue streams. First, you have enterprise compute contracts. These are massive multi-year deals with global corporations.
Okay.
Second are research partnerships, which are often funded by national governments or international scientific consortia. And third is the on-demand compute marketplace, where really well-funded startups can rent supercomputing time by the hour.
Let's do a deep dive into those enterprise clients, though, because understanding the industries driving this insatiable demand makes the whole premise click into place.
It really does.
Take the global finance sector, for example. We aren't talking about basic algorithmic day trading here. We are talking about moving from overnight batch processing to continuous real-time risk simulations.
Yeah.
Picture a massive investment bank managing a global portfolio.
Hmm.
They need to run what's called combinatorial optimization.
And the mechanism there is just fascinating because it's not just calculating one single variable, it's testing millions of interconnected variables simultaneously.
Like the butterfly effect.
Exactly. If the interest rate in Japan ticks up by a fraction of a percent, how does that cascade into European shipping logistics, which then affects tech stocks in California?
They're essentially trying to simulate the entire global economy in real time just to balance the risk exposure.
And you simply cannot run that math on a standard server rack.
No way. And then look at pharmaceuticals. The traditional drug discovery process is agonizingly slow. You physically mix chemicals in a lab, put them in a petri dish, and see what happens. It takes years and billions of dollars in failed physical trials.
It's so inefficient.
But with a compute campus, they run molecular dynamics simulations. They can simulate how millions of candidate molecules interact with a target protein at the atomic level.
Using the whole hybrid system?
Yes. They use the AI accelerators to filter out millions of bad candidates instantly, and then they use the quantum routines to understand the precise electron bonding of the finalists. They do all of this in a simulation before they ever touch a physical test tube.
And the ability to filter out a toxic compound digitally rather than discovering it during a $100 million clinical trial, I mean, that is worth an absolute fortune to those companies.
Absolutely.
The third major driver he mentions is global logistics. Think of a major shipping conglomerate or an international airline. They are dealing with a totally different kind of combinatorial optimization.
Oh, yeah. Like, imagine standing in a massive global shipping yard. You have to load 10,000 giant shipping containers onto a vessel. But you have to optimize for weight distribution so the ship doesn't burn excess fuel.
Right.
While also ensuring that the containers needed at the very first port of call are loaded on top, all while factoring in the refrigeration needs of specific containers.
It's a massive puzzle.
Or routing 500 airplanes while instantly adapting to unexpected weather systems, crew union rules, and fuel costs. In those industries, a 1% efficiency gain on a global scale saves hundreds of millions of dollars.
Which means they will gladly pay $50 million for the compute power to find that 1%. But there is a massive hurdle here, and Nishant talks about this. You cannot hand a logistics yard manager access to a raw quantum processor and just say, good luck, figure out the code.
Yeah, that's not going to end well.
No. To attract these incredibly lucrative enterprise clients, the campus requires a secret weapon. It requires an extraordinary software layer.
This is where the magic really happens, because the hardware is basically useless without the translation layer. The book highlights orchestration tools like Kubernetes and enterprise platforms from companies like Red Hat.
Basically, the ultimate automated air traffic controller for data.
Exactly. It acts as an invisible translator, completely hiding the terrifying complexity of the hybrid hardware from the user.
Right. The end user experience has to be totally seamless. A pharmaceutical researcher doesn't need to know how to program a quantum laser cutter.
No.
They just log into a clean interface, they select the molecular simulation library, input their chemical data, and hit run.
It is the software layer that makes all the complex decisions behind the scenes.
Yeah.
The software says, okay, send the massive data sorting task to the classical HPC manager, wrote the pattern recognition work to the AI forklift GPUs, and send this one specific complex probability calculation down to the quantum lab.
And the user has no idea their single click just bounced between three completely different paradigms of physics.
It's incredible. That software abstraction layer is the bridge. It turns a terrifying experimental laboratory of physics into a highly profitable, usable commercial product.
So the picture is really coming together now. We know what needs to be built, the massive 150-acre hybrid campus. We know how the capital works, the modular airport approach. And we know who is paying the massive operational bills, finance, pharma, and logistics.
So what's left?
Well, the final piece of the puzzle Nishant lays out is geography. Where on the map are these massive heavy industry projects actually going to be built?
Right. And Nishant points very specifically to India as a natural, almost inevitable hub for the next generation of global compute campuses.
And importantly, he backs this up with structural physical realities, not just geographic optimism.
Yeah, let's look at the mechanism of that ecosystem. Because as we established earlier, you can't just put these things anywhere.
No.
First, there's the energy requirement. India is currently undergoing a massive nationwide expansion of both solar parks and nuclear baseload energy. And you really need that synergy.
You need both.
Right? You need the cheap, abundant daytime power of massive solar fields, combined with the 247 unwavering stability of nuclear generation, to feed a 200-megawatt campus without crashing the local grid.
And then you look at the human capital. India has this globally recognized engineering workforce that is currently dominating enterprise software.
Absolutely.
But there's this natural ongoing shift where that talent pool is moving from managing global enterprise IT systems to managing complex 247 physical infrastructure operations.
They're adapting.
Yeah, they have the density of talent required to build and maintain those critical software orchestration layers like Kubernetes that we just talked about.
Plus, just the sheer economics of the physical space.
Mm-hmm.
Acquiring 150 acres of industrially zoned land with massive water rights is significantly more viable there than trying to wedge a campus into like Silicon Valley or Western Europe.
All possible.
Yeah. And the global hyperscalers, the massive cloud providers, they're already rapidly expanding their standard data center footprints across India. So the foundational ecosystem is already seeding itself.
Setting the stage.
Exactly. And Nishant points out that the geography within the country provides these specialized zones. So you have regions like Gujarat with deep industrial port infrastructure and massive renewable energy projects.
Okay.
You have areas like Tamil Nadu combining advanced manufacturing capabilities with strong wind generation.
Yeah.
You've got Telangana with the Hyderabad Tech Hub, and Karnataka providing the concentrated software engineering research talent in Bengaluru needed to tie it all together.
And this combination of energy, land, and talent leads Nishant to introduce perhaps his most profound concept in the book, the compute export industry.
Exporting digital steel. I love that concept.
Yeah. It is a total paradigm shift. Historically, a nation exports physical manufactured goods or natural resources. But in this new era, India wouldn't just be building these massive campuses to host its own domestic apps and data.
Right.
It would literally export computational capability to the rest of the world.
That's wild to think about.
Yeah, so a logistics startup based in Europe could remotely train their massive AI models on an accelerator cluster physically located in a 150-acre facility in Gujarat.
Wow.
A pharmaceutical research team in North America could run their complex molecular simulations on a hybrid platform halfway across the globe.
So the workloads just travel instantly across global subsea fiber networks. The heavy thermodynamic calculations happen on the Indian campus, and the insights are exported back.
Exactly. It turns pure computation into a premier global export commodity.
Man. So bring this all together for you listening. We've covered an immense amount of ground today. We started by dismantling the myth of the standalone magical quantum computer.
The God machine.
Yep. We've seen that the reality is the hybrid compute campus, a massive, coordinated factory floor of classical managers, AI heavy lifters, and quantum specialists all working in tandem.
It's incredible.
And thanks to Nishant Prabhakar's rigorous private equity analysis, we now understand that the future of technology isn't just about weightless code, it is incredibly heavy.
Literally heavy. Yeah.
It's about pouring concrete, laying steel, securing hundreds of acres of land, and battling the thermodynamics of hundreds of megawatts of power.
It truly is the ultimate infrastructure and capital play of the 21st century.
And understanding this physical shift gives you a massive analytical edge. Tomorrow, when you hear about a new artificial intelligence model or a quantum breakthrough in the news, you aren't going to just look at the microscopic chip itself.
No, you'll know better.
You're going to look past the chip. You're going to look at the massive physical infrastructure, the liquid cooling loops, the energy grids, and the billions of dollars of patient capital, making that single calculation possible.
Which leaves us with one final critical question to consider, building off of Nishant's thesis here.
What's that?
Well, if raw compute power is truly the ultimate economic engine of the 21st century, if it really is the new heavy industry, and certain nations are actively racing to build these massive campuses, what happens to the countries that fail to build their own?
Oh, wow.
Right. Do they become entirely digitally dependent on external compute superpowers? Much like nations without natural resources were completely dependent on oil-rich nations in the 20th century.
That is a fascinating parallel.
It's definitely something to think about.
The digital revolution was supposed to be invisible, but it turns out the future of the digital world is built on concrete, steel, and megawatts. Keep your eyes on the heavy infrastructure. We'll catch you on the next deep dive.